Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Now your ultrasound, how they produce image is very much different from your x-rays. In your x-rays, we rely, okay, let's say this is a part of your body, we rely on the x-rays passing through the body and coming out and darkening the film right now. So let's say there's a film here, so you will use it to darken the film. But for ultrasound, we don't use this technique. Ultrasound, if you have your body medium like this, so you got different boundaries. So let's say this is fat, this is muscle, and this is bone. So what the ultrasound does is, at every boundary, so that means at this boundary between fat and muscle, when the ultrasound reaches, you want a bit to be reflected. Then it continues, at the boundary between muscle and bone, again another one is reflected. So we actually rely on the amount reflected here to give you an image of what's happening inside your body. Right, so how much will enter and how much will be reflected is given by this relationship. Whatever ultrasound that we send in, some will be reflected and the balance will be transmitted, right now. So ideally, we want more to be reflected or more to be transmitted. More to be transmitted. We just need a tiny amount to be reflected so that we can form an image. We want most to be transmitted so that it can go deeper and deeper and deeper. If it reaches a boundary, everything is reflected, then practically nothing can go in anymore, because very little left over. So we want only a tiny amount to be reflected. The amount reflected is governed by the equation IR over I equals to Z2 minus Z1 squared over Z2 plus Z1 squared, where your Z is called a specific acoustic impedance, which I gave you the definition now. So specific acoustic impedance is Z equals to rho times C. So your rho will be the density of the medium, C will be the speed of the ultrasound through that medium. So each medium will have its own value of Z because it depends on the density of the medium. So every medium like fat, muscle, bone all have different density. The speed of wave also different, so therefore they have different values of Z, which is given in your next page. But you must notice the formula here. Since we want only a tiny amount to be reflected, that means this fraction must be big or small? Must be very small. For this fraction to be very small, the values of Z2 and Z1 must be almost the same. The bigger the difference between Z2 and Z1, the bigger the amount will be reflected. Do you understand? So we want these two to be almost the same. If these two are very different, then most is reflected. That means very little will be transmitted, which is bad. Okay? So, I'll show you. Okay, so for example, if you are using your ultrasound to scan the human body, do you know they always use a water-based gel before they actually put the ultrasound transducer onto your skin? Like for example, have you seen like pregnant ladies being scanned? Never, okay, but if you have seen, they will put a water-based gel, then they'll put the transducer on top. So why? Because without the water-based gel, then the boundary will be between air, which is this one, 430, and skin, which they take as soft tissue. So can you see air and soft tissue, the values are very big? Difference, big difference. If you substitute inside here, you will get IR over I as 0.99 something. That means almost 1. What does it mean? Everything that you send in, almost everything is actually reflected. Nothing goes in really. Which is why they must use a water-based gel. If they use a water-based gel on your skin first, then the boundary will be water and soft tissue. So water and soft tissue, the values are very similar. So you will get 0.00 something or 0.0 something, something like that. Very small value. So in other words, very little is reflected and most of it is transmitted. Now, if you look at bone, bone is the biggest value in your body. When I ask you what are the two biggest values for specific acoustic impedance. Some of you all gave me quartz, but quartz is not in your body lah. In your body will be bone and muscle. So what will happen is, when they want to scan your bone, it has to pass through muscle first. So the boundary will be muscle and bone. So can you see there's a big difference, 1.7 and 5.6 to 7.8? So because there's a big difference, a lot will be reflected at the boundary. That means very little actually goes in. So this is the first reason why we cannot scan structures within the bone, because very little actually can go in. Understand or not? Right, so that's the first reason. So this formula will tell you how much is reflected. Okay, then next we're going to talk about how much is transmitted. Now, the amount that is actually transmitted will be this value, but then it will pass through your medium of thickness X. And so when it passes through a medium of thickness X, some of it will be absorbed. So what comes out finally is what we want to calculate. So what comes out finally is given by the equation I equals to I naught E negative Kx, where X is the thickness of your medium, like your bone or your fat or your muscle. K is called the absorption coefficient, which is given to you. And the absorption coefficient is similar to the linear attenuation coefficient or linear absorption coefficient in X-rays. Remember when we studied attenuation of X-rays, we also use a formula similar to this, but we use mu, right? So now we use K. So the K here is just called absorption coefficient. So the higher the K, the more is absorbed or the less is absorbed? The more is absorbed. So I show you some typical values. So if you look at the typical values here, the ones with highest values will be bone and air. So what does it mean? Because your bone and air has big values, that means a lot will be absorbed, so very little will remain. That means for bone and air, this value will be very small. I over I naught ratio is also very small. So remember I was telling you cannot scan structures within the bone. Now this is the second reason, because assuming that very little actually manages to enter through the bone, but because the absorption coefficient is so big, practically everything will be absorbed. So nothing can come out and give you an image. So therefore you cannot see what's happening. Now on top of it, why is it bad? Now there's also a side effect. If your bone absorbs all the ultrasound, the CAIE will go up right now, because ultrasound is vibration of atoms or molecules. So the CAIE will go up, so the temperature will go up. So what it means is the cells in your bone will start to heat up. And when that happens, the dissolved gases in your cells will start to boil. And when they burst, when the cells burst, it will cause damage lah. So it could cause the same ionizing effects or side effects to your body, just like X-rays, like ionizing radiation. So it actually causes damage to your cells or even destruction of your cells. Which is why we don't use ultrasound to treat anything near your bone. For example, do you know that ultrasound can be used for treatment of sports injuries? Let's say you have a muscle torn muscle. They can actually use ultrasound, put it near your muscle, and as it heats up, it will draw blood into your muscle. So that carries along with it nutrients and oxygen, so it tends to heal faster. But if your joints have problem, they won't use ultrasound to treat. You know why? Because your joints are too near your bones, and that causes side effect. Do you understand? So the other thing that they cannot scan is anything in your body that has air. So which part of your body has the most air? Lungs. So inside your lungs, we cannot see what's happening if you're using ultrasound. That's the bad thing. But the good thing about ultrasound, it is portable and it's quite cheap, relatively cheap. Okay? So whenever you want to calculate how much will come out after being absorbed, you use this. If you want to calculate how much is reflected at the boundary, we use the previous equation. So for an ultrasound, what actually happens is the ultrasound will pass through the body, and at the boundary between two medias, it will actually be reflected. So let's look at an example here, which is let's say you want to scan the head of a person. So let's say this is the head. Look from the top. So inside, got two parts of the brain, the left brain and the right brain. Okay, so what will happen when you scan it? Okay, by the way, let me just draw the skull first. But of course, there's not so much big gap one. I'm just drawing just to show you. And so what will happen is when the ultrasound touches, the transducer touches your skin, there will be a reflection at the boundary. Remember where they put the water-based gel? So at the water-based gel there will be a reflection here between the water-based gel and your skin, so there's a transmission pulse. Then it goes to your skin, your scalp, and then your skull, all these are here. Then it goes into your brain here, let's say the left brain here. Now why is this empty? It's not because there's nothing in the brain, but because there's no boundaries between anything here, because it's just the same medium. Then it goes to your midline fissure, the median fissure here, so there's a reflection. Then it goes to the other side, the other part of the brain, and then it comes out from the other side, the skull and the scalp and all those. Now, how is your A scan used to give you information? Because we don't see any pictures right now. It doesn't even look remotely like a brain right now. Because if, let's say, the person has a growth within the brain, you will see additional peaks. Because the ultrasound will have to enter and come out. So you will have two peaks, one when it enters and one when it leaves. Because this will be a boundary. Understand? So depending on what is the medium here, it will give you different amplitudes. If it is just a small blood clot, because blood is not very dense, then the amplitude will be small. So you will probably see a very small amplitude. But if, let's say, this thing here is actually a tumor, which is very dense, then you see a very big amplitude. So that's what we mean by the strength of the echo indicates the nature of the boundary. Okay? But also, if let's say you put it in muscle or fat or bone, but bone cannot because bone cannot penetrate, right? But if you're using muscle and fat, then you can find out the thickness of muscle and fat. How do you find out? Okay, let's look at another thing. Since this is a CRO, by the way, so I forgot to tell you that this image that you see is actually a CRO. That means when the ultrasound transducer is placed on your skin, it's actually connected to a CRO. So all these pulses that come back are displayed on a CRO. And on the CRO, there's a time base, right? So you can actually find the time between two peaks. How you find the time between the two peaks? You take the number of divisions, then you multiply by the time base, then you get the time between the two peaks, right? So let's say you want to find the thickness of this tumor, example. So the thickness, which is the distance, will be your speed times time. Agree not? So you must know the speed of the ultrasound through this particular medium, and you must times the time taken for it to travel through the medium. Now, assuming that the time between these two peaks is t, when you want to multiply to get the distance, the t that you use, you must divide by 2. Why? Because the first time you get a peak is when it enters. The second time you get a peak is when the ultrasound goes in and then comes out again, and then you get the second one. So that means the time between the two peaks is for the ultrasound to go and come back. But you want to find the thickness, you just have to find the time taken to just go in only. Because the speed times time equals to distance. So always remember to find the time here, but you need to divide by 2 first, before you multiply by your speed to find the thickness. Okay?
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with 1 or 2 past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.